You click a link and poof, a website appears. It's something we do 100 times a day without a second thought. But have you ever really stopped to think about what's happening behind that click? It's this incredibly complex, honestly beautiful system. So today, we're going to pull back the curtain. We're going to follow that single click on its journey across the entire world and back, all in the blink of an eye. I mean, this is really the core question, isn't it? How does your little request travel, thousands of miles, find the one right computer out of billions, and then bring an answer back to you in less than a second? It feels like actual magic, but it's not. It's just a truly incredible feat of engineering. All right, so how do we even begin to unpack this? Well, the first thing we got to understand is how your data gets from point A to point B. And the best way to think about it is like a digital postal service. It's got its own special way of sending and delivering mail.
Okay, so there are basically two ways you could send a big message. On the one hand, you have the old way, circuit switching. Just think of an old school telephone call. You get a direct, dedicated line just for your conversation. It works, sure, but it's not very efficient, especially for something as massive as the internet. So what the internet does instead is something called packet switching. And this idea it's just brilliant. Instead of sending one huge file, imagine you want to mail a book. You tear out every single page, put each page in its own separate envelope with an address, and then just dump them all into the mail system.
And this, right here, this is the whole game. Packet switching is literally the ingenious trick that makes the modern internet possible. It's how billions of us can all be online at the same time, using the same network without everything grinding to a halt. It's a foundation for everything we're going to talk about next. So what does that journey actually look like for one of these packets? Well, first, your message, let's say it's a photo of your cat, gets chopped up into these small, manageable packets. Then, whoosh, they're all sent out into the wild network. And here is the really cool part. They don't have to stick together. Each packet is a free agent. It can take a totally different path to the destination, always looking for the quickest route. And then, at the other end, the system gathers them all up and reassembles them in the exact right order. So your cat photo looks perfect. Okay, so we've got all these little digital envelopes zipping around the globe. But wait a minute, how do they know where to go? And how can a computer in Japan talk to a server in Brazil? Well, just like people, they need a common language, a shared set of rules of the road. In the tech world, we call these protocols. And it all starts at the very bottom, with the physical stuff, the actual wires. I'm talking about the massive fiber optic cables stretched across the ocean floor, the Ethernet cable plugged into your wall, even the Wi-Fi signals buzzing through the air. This layer's only job is to turn your digital bits into real-world things, like pulses of light or electrical signals, and just get them moving. Now, sitting right on top of those physical wires is where our digital postal service really comes to life. This middle layer is all about logistics. It's responsible for the addressing and the routing of all those packets. It's basically making sure messages get from the client to the server, that all the packets are in the right order, and that the whole flow is under control. And then, finally, at the very top of this whole stack, you've got the layer that actually interacts with you and your apps. This is kind of like a universal translator. Its job is to take all that reassembled data and resolve any differences in format, making sure your web browser or your email client can actually understand and display the final message. This is what makes it all useful to us humans. So, what are the specific tools our digital postal service uses? Well, first, every single device on the internet has a unique IP address. That's its street address. It also has a MAC address, which is like a unique serial number for its hardware. Now, you and I aren't going to remember long strings of numbers, right? That's where DNS comes in. The domain name service is basically the internet's giant address book. It translates a friendly name we can remember, like google.com, into that numerical IP address. And the routers? They're the mail sorters, the traffic cops, directing all the packets along the best possible path to their destination. Okay, this all sounds great. It's an amazing system, but it's also incredibly complex. And with complexity comes failure. Things go wrong. A cable gets cut by a ship's anchor, a server overheats and crashes. So what happens then? Well, here's another beautiful part of the design.
The internet was built from the ground up expecting things to break. And to handle this, to detect these failures, systems use a really clever little trick called a heartbeat protocol. And it's exactly what it sounds like. It's a way for connected computers to constantly check in on each other, to feel for a pulse, and make sure everything's still working. It's pretty simple, actually. Let's imagine you have two systems talking to each other. We'll call them Site A and Site B. Every so often, at a set interval, Site A just sends a tiny message over to Site B that basically says, "I'm up."
Site B gets that little "I'm up" message, and all is well in the world. It knows Site A is online, the connection is good, and the conversation can just keep on going. Everything is humming along just as it should. But what if Site A sends its message and just hears silence? What happens then? This is that critical moment of uncertainty.
Well, it doesn't just throw its hands up and declare a catastrophe. No, it tries again. This time, it sends a more direct question, almost like it's leaning in and asking, "Hey, are you up?" It wants to be absolutely sure before it raises an alarm.
And if still there's no reply, okay. Now Site A concludes there's been a failure. It might not know exactly what went wrong. Maybe the server crashed or the connection is broken, but it doesn't matter. It knows enough to act. It immediately tells the rest of the network, "Hey, that path is dead, find another way." And just like that, traffic gets rerouted around the problem. That right there is the built-in resilience of the internet in action.
So let's put this all together. We've got data traveling in these little packets, following a common set of rules, and we've got a system that can heal itself when something breaks. How does all of this connect to the things we use constantly, like the cloud?
Right, so what is the cloud? It sounds so ethereal and mysterious. But really, when you get down to it, it's something called a distributed file system. Fancy name, but the idea is pretty straightforward. It's a whole bunch of storage devices, computers, all spread out, maybe all over the world. But they are managed in a way that, to you, they look and feel like one single normal file system. And these massive, hidden systems are built with a few key goals in mind. First, transparency. The whole point is to hide all the crazy complexity from you, the user. It should just work. Second, fault tolerance. This is what we just saw with the heartbeat protocol. If one piece fails, the whole thing keeps on chugging without you ever knowing. And third, scalability. As more people use the service, they can just keep adding more computers to the system to handle the load. And really, that first goal, transparency, that's the whole magic trick. There's this great quote that sums it all up. The distributed system should appear as a conventional centralized system to the user. All that amazing complex stuff we talked about, the packets, the routers, the heartbeats, it all exists for one reason: to create an experience for you that feels completely simple. So, what's the big takeaway here? The internet wasn't designed to be perfect. It was designed to be resilient. It was built to be decentralized and to always find a way around failure. And that kind of leaves us with a final, bigger question, doesn't it? What can we learn from that design philosophy in our own connected lives and in the other systems we build?